It was supposed to be one of NASA's greatest triumphs, a powerful new rocket engine that could redefine space exploration. Years of research, millions of dollars, a machine designed to reach the stars. But just seconds after ignition, something went wrong. The temperature spiked, the metal began to warp, and before anyone could react, the rocket melted itself. What followed was one of the most embarrassing and least talked about engineering failures in NASA's history. A rocket so ambitious, so powerful, and yet so catastrophically flawed that it burned itself out before ever leaving the ground. This is the untold story of the rocket that melted itself, a cautionary tale about innovation, failure, and the thin line between genius and disaster. In the early days of space exploration, one thing mattered above all: thrust. To reach orbit, escape gravity, or send humans to the moon, rockets needed to produce unimaginable power. NASA engineers pushed the limits of technology, experimenting with liquid hydrogen and liquid oxygen, propellants that burned at thousands of degrees. By the 1960s, after the success of the Saturn V, the world's most powerful rocket, scientists were dreaming even bigger. They wanted engines that could take astronauts beyond the moon, to Mars, even further. And that's when the idea for a new, experimental engine was born. Its name, the F-1A hydrogen booster, an upgraded descendant of the mighty Saturn V engines. But this wasn't just another test. It was supposed to be the future of NASA propulsion. The F-1A was built for raw power. Each engine would generate over 1.8 million pounds of thrust, enough to lift a skyscraper. It used a combination of liquid hydrogen and liquid oxygen, burning at temperatures so extreme that almost no known material could survive direct contact. The design was cutting edge, using complex cooling channels to circulate cold fuel through the engine walls, keeping the metal from melting under the fiery inferno of combustion. It was elegant, ambitious, and dangerously close to the limits of physics. Engineers knew that even a tiny imperfection, a bubble in the fuel, a crack in the nozzle, could lead to catastrophic failure. Still, they pressed forward. Because this was NASA, and failure wasn't an option. It was a clear morning in 1967 at the Marshall Space Flight Center in Alabama. Technicians double-checked every valve, every sensor, every bolt. Hundreds of spectators and engineers gathered to watch history in the making. Countdown. 3, 2, 1. Ignition. A thunderous roar split the air. The engine came alive, flames pouring from the massive bell nozzle. At first, everything looked perfect. But within seconds, sensors began to register rising temperatures, far higher than expected. Something was wrong. Inside the combustion chamber, turbulent pressure waves were forming, tiny oscillations that caused the flame to pulse and distort. In an instant, the vibrations grew out of control. The engine's inner walls, meant to be cooled by the fuel, began to glow red-hot. Then, meltdown. Metal warped, valves burst, and molten fragments sprayed across the test stand. The rocket had literally melted itself from the inside out. When the smoke cleared, the damage was staggering. The engine's interior was destroyed. Millions of dollars of equipment were gone in seconds. NASA's top engineers were stunned. The agency that had sent humans to the moon was now facing one of its most humiliating failures. Early analysis showed that the extreme vibrations, known as combustion instability, had caused localized overheating. Essentially, the rocket had created a self-amplifying resonance, a feedback loop of heat and pressure so violent that it cooked itself alive. It wasn't a design flaw in one part. It was a flaw in how the entire system behaved at high power. The engineers called it the beast inside the chamber. Rather than cover it up, NASA treated the failure as a priceless lesson. They launched a series of follow-up tests, using high-speed cameras and pressure sensors to study the oscillations. What they learned would change rocket science forever. They discovered that combustion instability wasn't just a problem of materials. It was a mathematical chaos problem. At certain frequencies, pressure waves in the fuel mix could align perfectly, creating destructive harmonics that tore engines apart. To fix it, NASA developed new simulation models, and engineers designed baffles and injectors to break up these pressure waves. Those innovations would later make engines like the Space Shuttle main engine and RS-25 far more stable, capable of surviving conditions that would have melted earlier designs. So while the F-1A disaster was devastating, it helped prevent far worse failures in the decades that followed. In the grand story of space exploration, the rocket that melted itself is barely mentioned. It never flew, never carried astronauts, and never made headlines. But its legacy lives quietly inside every modern rocket engine. Because sometimes, progress doesn't come from success. It comes from the courage to fail, analyze, and try again. The F-1A engine never reached space, but it helped NASA build the knowledge that powers today's missions to Mars and beyond. So, the next time you see a rocket light up the night sky, remember the one that never left the ground. The one that melted itself so humanity could learn how not to. The story of NASA's melted rocket isn't just a technical failure. It's a reminder that science moves forward one mistake at a time. For every launch that succeeds, there are a dozen forgotten tests that didn't. And each one left behind a clue that made the next mission possible. That's how progress really works, through sparks, fire, and sometimes molten metal. Thanks for watching. If you enjoyed this story of engineering and discovery, be sure to like this video and subscribe for more deep dives into the history of science and technology.